Hello everybody. So in this video we are going to solve one more example on the combustion reactions, and in this case we have a mixture of octane and hexane. So octane is known to be C8H18 and hexane is C6H14, and the mixture is 100 moles per hour. It contains 75 mole percent octane and the balance is hexane, which means that octane is 75 moles per hour, the flow rate of octane in the fresh feed, and the flow rate of hexane is 25 moles per hour. And it's burned with 40% excess air in a furnace. So this is the feed of the fuel, the octane and hexane, and this is the feed of oxygen and nitrogen. We know the percentage excess, but we don't know the actual amount now. Both components are completely consumed in the reactor. This sentence doesn't have anything to do with the combustion, whether it's complete or incomplete. This sentence is about the conversion. So this is the conversion of both hexane and octane. So they are totally consumed, meaning that there is no octane and hexane in the product stream. And this is why in the product stream we don't have any octane or hexane. It's only the unreacted oxygen, nitrogen, and the reaction products. All hexane is completely burned, while incomplete combustion takes place to 25% of octane. So for hexane, it's only complete combustion reaction, but for octane we have complete and incomplete combustion for octane. We need to calculate the molar composition of the stack gas. Stack gas is the product gas, or the combustion effluent gases on a dry basis. So this is I think this is very similar to the previous problem. The only difference is that we have a mixture of two different fuels. It's not only one pure fuel. So in this case we have let's start with the first things first. So we have the flow chart. Stream numbers are there. We have the components on each stream. We haven't missed anything. We have 5 components here: oxygen, nitrogen, and 3 products. We don't have any octane and hexane because they're totally consumed. So now we can write the reactions that we have. So the reactions are, as we agreed, there are 2 reactions for octane: the complete and incomplete combustion, and the complete combustion for hexane. So for octane, these are the 2 reactions that we have, and I think the balance now is not a big deal. You can do it yourself. And for hexane, it's only the complete combustion reaction. So we have the 3 reactions that are taking place inside the reactor here. And now let's write the additional relations that we have. So from the beginning, we have the 75 is already on the diagram. So I already used this information. The first is that we have 40% excess air. The second is that it's air. So we have nitrogen to oxygen is 79 to 21. So we know the ratio of oxygen to nitrogen. And now we have the 25% of octane burned incompletely. This information. I'm going to put it this as it is here, and then we are going to see how to deal with it when we write the equations. But we understand that this is an additional relation. So if we have all the additional relations, we are not missing anything. So we can do the degrees of freedom analysis. We can do it by calculating the number of variables. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 variables. And if we are doing this using the extent of reaction method, so we have 3 more variables. So it's 9 plus 3. The given variables are 2. I have only 2 variables. So it's 9 plus 3 minus 2. The number of equations, it will be for octane, hexane, oxygen, nitrogen. So these are 4. Carbon monoxide, carbon dioxide, and water. So this is 7. And for the additional relations, we have 3. So this is 9 plus 3 minus 2 minus 7 minus 3, which is 0. So the system is solvable, and we can calculate the unknown variables. So again, as we agreed last time, I have all the relations and the equations on the right side so that they are available in case I need them. And now we can start with the solution. We have, as we said in the degrees of freedom analysis, we have 7 equations and we have 3 additional relations. So I would as I mentioned last time, it's better to start with the additional relation 1 and 2 because they will be very direct, very straightforward, and you can use them to calculate the flow rates of the components in stream number 2 directly. So again, for the excess air, we have to know the theoretical amount of oxygen, and from the theoretical amount of oxygen, we can calculate the actual amount of oxygen, and from the ratio, we can calculate the actual amount of nitrogen. But here there is a tricky part here, which is the way we calculate the theoretical oxygen. And just to make things clear, let's go back to the definition. The theoretical oxygen is the amount of oxygen that is needed so that complete conversion of the fuel takes place. So all the fuel is burned completely. So all the fuel will completely burn to produce carbon dioxide and water vapor. So the oxygen needed for this is the theoretical oxygen. It doesn't matter if it's 1 or 2 or 3 components or 3 different fuels in the same place. You can do it for all of them and get the sum of the oxygen needed for all of them. And it doesn't matter if in reality we have incomplete combustion. So this is one thing that makes people kind of confused. So we already have incomplete combustion here. So should I calculate the theoretical oxygen using this or using this? From the definition, it is the oxygen needed to consume all the octane and all the hexane completely in complete combustion reaction. So I'm only using this and this. It's a theoretical amount. So the theoretical amount assumes that the ideal case is taking place, which is that all the fuel is consumed in complete combustion reaction. So I hope this is clear because it causes a lot of confusion. So under these conditions, we can calculate the amount of oxygen needed for reaction 1 and reaction 3. Okay, I'm not saying that this is what these are only the reactions that are taking place, but this is what I use to calculate the theoretical oxygen. And I already know that there are 75 moles of octane and we have 25 moles of hexane, so I can easily calculate the amount of oxygen needed to completely burn these two fuels. So 75 multiplied by 12.5, so these are the number of moles of octane and hexane, so it's 75 times 12.5 plus 25 times 9.5. So this is the theoretical amount of oxygen, and I'm going to use the 40% excess, so it is 1 plus 0.4 multiplied by 1175 will give us the actual amount of oxygen that we are going to use, which is the flow rate of oxygen in stream number 2. From the second additional relation, we can calculate the number of moles of nitrogen that we are going to use in stream number 2, which will be the last information we need to fully define stream number 2. So I have already used the two additional relations, and I calculated two variables. Now we can move forward to calculating the product stream flow rates. We have still one additional relation that we haven't used, and we have 7 balance equations. So let's start with the mass balance on the furnace. So the mass balance, we can start with carbon monoxide, and the reason I started with carbon monoxide is that we have an additional relation, the third one that can be used, and I'll keep it for the end. But for carbon monoxide, it is the carbon monoxide out equals the carbon monoxide in. We have no carbon monoxide here, and carbon monoxide is only part of the second reaction, so it is plus 8 Xy2. So it is I can calculate the value of Xy2. I don't know how I got this Xy2. This is confusing. So we should use this relation to calculate the number of moles of carbon monoxide. So let me just say it. I think there is something about the slides here, or in the slides, that is not written. Maybe I forgot. Oh yeah, it's here. So from the relation, I'm sorry, it's just a problem with the animations sequence. So for this relation, we have that 25% of octane is completely is burning incompletely. So I know the number of moles of octane that are contributing to this reaction. So I know all the octane is 75, and 25% of the octane, which is 0.25 times number of moles of octane in stream number 1, is going to be here, and I know that each one mole of them will produce 8 moles of carbon monoxide. So I can calculate the number of moles of carbon monoxide by multiplying the number of moles of octane contributing to the incomplete combustion reaction multiplied by the ratio of number of moles of octane to number of moles of carbon monoxide. So this will give us the number of moles of carbon monoxide in the product stream. And from this and the balance on carbon monoxide, we can find the value of Xy2. So this is how we got this value of Xy2. Now we can write the balance equation on octane. Octane is totally consumed, so the product is 0, and the 0 equals the octane in the feed, which is 75, and it's consumed in reaction 1 and 2, so it's minus Xy1 minus Xy2, and I know that the value of Xy2, so I can calculate Xy1. Now we can move to, so I calculated now the two extents of reaction, which is good news as we agreed. And we need to calculate Xy3, and Xy3 we can get it by writing the balance equation on hexane. So for hexane, the product is 0 and the feed is 25, and the hexane is only consumed in stream reaction number 3, and the coefficient is -1, so it's number of hexane minus Xy3. So this is 25. We can now calculate Xy3, and this is very, very good news. Once we know the 3 extents of reactions, we can calculate everything else. So for the rest of the components, we can write the balance equation on carbon dioxide. So carbon dioxide is a product in reactions 1 and 3, so it is the feed is the product equals what is in the feed, which is 0 plus 8 Xy1 plus 8 plus 6 Xy3, so this is 600 moles per hour. For water, it is product of the 3 reactions, so it is 9 Xy1 plus 9 Xy2 plus 7 Xy3, which is at 150 moles per hour. And for oxygen, it is what we have in the feed, which is 1645 minus 12.5 Xy1 minus 8.5 Xy2 minus 9.5 Xy3, which is 545. So it's done. We have already calculated everything here, and of course nitrogen in the feed is the same as nitrogen in the product. So we are not I'll keep this after I finish this. So we are not doing any extra calculations for nitrogen. This is the same number of moles of nitrogen in the product, and now we calculated everything: carbon dioxide, oxygen, nitrogen, carbon monoxide, and water vapor. So we have everything here. We can write the same, also solve the same problem using the atomic balance method. Again, I'm just doing this to show you that you can get the same results. So with the atomic balance method, if we do the degrees of freedom analysis, we will have the same number of variables, but we don't include the reactions, so it is just 9, and the number of equations is going to be different. We have oxygen, nitrogen, carbon, hydrogen, just this: oxygen, carbon, hydrogen, and nitrogen. So we have 4 equations. So now if you calculate the degrees of freedom, it's going to be 0, which is the same. And for the additional relations, we agreed that they are the same regardless the method that we are using. So we are getting the same outputs from the 3 additional relations: number of moles of oxygen, nitrogen, and the product carbon dioxide. And now we can write the balance equations. We can, and this is I think this is the most tricky part in the atomic balance, is which equations should we start with. So you need to look for the equation that contains the least number of unknown variables. So for nitrogen, we know that nitrogen is going to be in equals out. So we now easily calculate the number of moles of nitrogen in the product stream. Now we have oxygen, carbon, and hydrogen. Hydrogen is only here. Carbon is only in these 2, and oxygen is in the 4. So we will keep oxygen till the end. We can use hydrogen to calculate the number of moles of water. We can use carbon to calculate the number of moles of carbon dioxide, and at the end we can use oxygen to calculate the number of moles of oxygen. So for carbon, it is, again, we have nothing to do with the reactions. So it's 8 times 75 plus 6 times 25. This is the number of moles of carbon in the feed, and the product we have the carbon dioxide that we calculated, 150 times 1 plus number of moles of carbon dioxide times 1, so we can calculate the number of moles of carbon dioxide in the product stream. For the hydrogen, we have hydrogen here, we have 18 times number of moles of octane, which is 75, and 14 times 25, this is what we have in the feed, and the product is just the number of moles of water times 2, so we can calculate the number of moles of water. Finally, we can write the balance on oxygen, and from this, and here is the equation, and you can use it to calculate the number of moles of oxygen in stream number 3, which is everything. So now we calculated all the flow rates of all the components in the product stream, and this is the summary of results. These are the flow rates and the compositions of the feed components, oxygen, nitrogen, hexane, and octane, and these are the mole fractions and the flow rates on wet basis, and these are on dry basis. So this is almost or this is summary of all the results, and this is the end of chapter 4, and finally we are done with this chapter. And as I mentioned before, I'm going to have or to record I think 3 or 4 more videos because there are some very important things that I want to include or discuss. Since I don't have the time limitations that I have in class, so I'm going to expand the things that we can cover regarding the degrees of freedom table and the mass balance for multi-unit systems. So I'm going to start this next time, and I'll see you then. Goodbye.